Hi, class. So what we're going to talk about now is mass spectrometry. Now, what this looks at is the mass to charge ratio. And this is really, really important because, as the title would suggest, usually you're looking at the mass of a molecule. But one of the things that tends to get lost is that it's the mass to charge ratio. And so we really care about the charge on a molecule, right? So what charge does it have? And the problem, especially as you move into biological molecules, is sometimes it can have multiple charges, right? So if something has a charge of 2, then remember, you're actually going to cut the mass in half, right? So you can have these giant proteins that actually would be thousands of molecular units, but because they have a bunch of charges, you actually see the mass be relatively small. So just be really, really careful that it's the mass to charge ratio and that Z is representing the charge. Now, typically we have to put the charge on the molecule somehow. Right? And so there's a couple different ways. One of the things that we tend to do is we tend to try to put a positive charge on it. All right, so we can do this by adding a little bit of acid. So we put a drop of acid and we protonate it. All right, so let me give you an example. If you have an amine, so your NH2, you put a little bit of acid. So our H plus is that example of some acid. It becomes NH3 with a positive charge. Now that Z value becomes 1. And so we can see the mass of the molecule. If your charge is 1, that's actually the easiest case because it's exactly that molecule. All right. Now, we can also do things where we hit it with electrons and put a charge on it that way. And so that's another way to do this. We won't spend a lot of time on it, but it's another good way to just put some charge on it. Now, one of the things that is a little tricky about this is it's very, very sensitive. And so it's a really, really good way to identify a molecule, because if you get down to several decimal points of the mass, it's actually very specific, right? And so unlike people who like our weight can kind of go up and down, a molecule is always going to be the exact same. So let's actually see what this looks like. All right, so if you have a mass spectrum, it's pointed where it's the relative abundance on the left, right? So on our y-axis, so how much of that peak is there? And then our mass to charge ratio across the bottom. Okay. What you're actually going to see is you don't tend to see just one peak. A lot of times you tend to see a lot of other peaks because this instrument tends to have a lot of high energy when it's bombarding the molecule or it's throwing it through the instrument. And so the molecule will start to fragment or break apart. Right? And so you see a lot of those fragments. In one way, this is actually really helpful because how the molecule breaks apart a lot of times tells us information about that molecule, like what functional group's in it, because things tend to break apart in a very predictable way. And again, we're just going to cover the mass spec very superficially, but it's actually a really, really useful technique. And a lot of biotech and pharmaceutical companies will send their new molecules through it so they can test to see exactly what's in the molecule or in their sample, and they can match up molecules. All right, so a couple different things. So our base peak is just the most abundant peak, right? So not necessarily the actual molecular weight of our molecule, it's just the most abundant peak. So let's look at the bottom. So here's our molecule, right? There's a benzene ring here in white in the middle, our alcohols, and then a carbon chain with an amine. So our molecular weight for this molecule is 153. So we see that molecular ion peak. So the molecular ion peak is the actual mass of that molecule, right? So that's how much the molecule actually weighs. It's our molecular ion. So that's the actual weight of our compound. The base peak, however, is the most abundant peak. Right? So as you see this, we set this to 100. And so that's the largest peak. Here's the actual molecular weight. And so we can actually see there's some fragment that fell off, right? So we could subtract these two numbers and try to figure out what that piece is that fell off. Right? And so a lot of times what we're going to see is alcohol groups tend to leave in the form of water. Things next to benzene rings tend to break off because benzenes are so stable by themselves. And so we're going to have different places we can actually cleave the molecules. So we'll talk a little bit about that. All right, so let me take you a little bit back to Gen Chem. So if you're looking at isotopes, Remember, we tend to see a weighted average on the periodic table. So a lot of times when you look on the periodic table, you'll see the molecular weight, and it's a weighted average of all the isotopes. And remember, by weighted average, we're taking the weight and the relative abundance, right? And we're using those two factors to come up with the molecular weight you see in the periodic table. What mass spec does is it actually looks at each individual atom. And so for carbon, the way this works is carbon 12 and carbon 13 are two isotopes we have, right? And so 99% of the carbon you have is carbon 12 and 1% is carbon 13. So that means if you shot a sample, 99% of those molecules would have carbon 12, one would have carbon 13. Which means if it's carbon 13, your molecule is actually going to be one mass unit higher. Okay? Same thing with chlorine and bromine. These ones are a little bit closer, right? So if we've set everything to 100, that means about a third of them are going to have chlorine 37, which means that you'd have a peak that's 2 mass units more. Bromine also is really characteristic because they're almost 1-to-1, right? So not quite, but really, really close. And they're 2 units apart. And so what you actually see when you have bromine is 2 twin peaks that are 2 mass units apart. And so we're actually going to talk about these because what we can see is this isotope pattern is actually going to give us a little bit of a fingerprint. It's going to highlight that we have that atom in our molecule. So let's take a look at some of these. All right, so let's see the peaks of chlorine and bromine. So the first one we're going to look at is chlorine. And so we just talked about the relative abundance, right? So chlorine has 75% is chlorine 35, 24% is chlorine 37. And do you see how these two mass units are 2 units apart? And so what we'll actually see is that we're going to have a ratio of the mass and the mass plus 2. All right, and that plus 2 comes from the difference here, right, of 37 minus 35. There's a difference of 2. And so it's those 2 extra mass units. These peaks will tend to be in a ratio of 3-to-1. So if we come over here, the peaks we're talking about are these 2 right here. And you see the 2 mass units that we're talking about? This one's 64, this one's 66. And so even though the mass is 64, this one comes from the 37 isotope of chlorine. And these 2 peaks should be in a ratio of about 3-to-1. And so it's that height, right? If we're looking at the height, this is about 33%. So it's about 3-to-1. And so what this should do is tell you that in this molecule, right, this group all together, sorry, I know I have a lot going on, right here should tell you that you have a chlorine. All right, it's going to tell you that you have a chlorine in your molecule. Okay. Let's look at one more. If you have a bromine, same idea, right? We have one of them that's about 50% and the other one's about 50%. They're 2 mass units apart because this one's 79 and this one's 81. So just like before, we'll have 2 peaks, one at 122 and one at 124. And that's only because of the example, right? More importantly, they're going to be 2 units apart, right? So it's always going to be plus 2, right? So that's where this m plus 2 equals, right? Or if we had something that's just adding a single proton, it'd be plus 1, right? So it adds 2. And what you should see from this is even though these peaks are little, you see how they're about the same height? So when you see these twin peaks, it should tell you that there's a bromine. Right? So we're going to have a bromine in our molecule. Right? And if you remember, this is my base peak. And I think if we add these up, right, what we probably see is that we got this base peak by losing the bromine, right? And so that bromine fell off and we got that peak. right? And so this is how we can start to get information out of our molecule that, yes, these peaks are great because they'll show us the molecular weight of our molecule. And so that would actually tell us, yes, we made that molecule, we can match up that mass, but it also tells you that you did a bromine, right? So that you have a bromine in your molecule. So if you did a reaction like this, where we add HBr to it, one thing we could do is put this on a mass spectrometer, and hopefully what we should see is that really nice bromine peak, right? And the bromine peak should add across it, and we get the bromine to our molecule. And so it should work really, really nicely in terms of showing this nice bromine peak here at the bottom. And then the other thing you should look for is halogens tend to fall off our molecules. We've talked about them being leaving groups, so they actually fall off. So a lot of times you'll see your base peak is the loss of that halogen, right? So we lose that hydrogen, that bromine or the chlorine. Last one. So a couple different things we can get from this is when you're looking at a mass spec, you want to look to see if you have that chlorine or bromine pattern, right? It's going to be the M+2, where M is the mass. So you have one peak where the mass, and then the other one would be the mass +2. And remember, that's for that second isotope. So in chlorine, it's 35 and 37. For bromine, it's 79 and 81. So we get those two different isotopes. And so one isotope is 2 units more. So that's why you should see the 2 peaks, right? And remember, for chlorine, it's going to be a 3-to-1 ratio of those 2 peaks. For bromine, it's pretty much going to be 1-to-1. All right, the next thing you should look for is the mass odd or even? If it's odd, right, meaning it has an odd molecular weight, it usually means it has a nitrogen. Now, if a compound has an odd number of nitrogens, meaning typically it has 1 or 3 or 5, it's going to have an odd value, right, in terms of molecular weights. Right? So when it's M/Z, it'll be odd. Now, the problem is, if you take 2 odd numbers, like let's say we took 1, if you add 2 of them, 1 + 1 = 2, it actually makes the molecule even. And it actually works out really well, right? Like if you take 5, 5 + 5 is 10, you still get an even number. So while this rule is really neat, if you have an odd number, it's going to tell you for your molecular weight, your M/Z peak, it means you have a nitrogen. But if you have an even number, it doesn't necessarily mean that you don't have a nitrogen, because you could have 0 or an even number. All right, so you have to be really careful. But what I would think about is if you have an odd number, it gives you a good hint that there probably is a nitrogen. One last thing, if you have a complete unknown, like you don't know anything about the molecule, someone gave you the sample and said, figure out what it is, kind of like we've done in some of our labs. What I would do is the rule of 13. Right? And so the way this works is once you've subtracted everything that you can figure out about it, right? So if we've used our mass spec and we see that this M+2 peak tells me there's a chlorine or a bromine, we want to subtract those masses, right? If there's an odd mass, we subtract the nitrogen. If you have an IR and you can see a carbonyl peak or an OH peak, let's subtract those oxygens. After you've subtracted all those other atoms that you can figure out from other pieces of information, you want to divide the mass by 13. And what this is going to give you is a very rough estimate of the number of carbons. And where that number 13 comes from is carbon has a mass of 12, and you're going to have at least 1 hydrogen, right? On most carbons, every now and then you can have a quaternary one, so there's no hydrogen, but you're probably going to have at least 1, probably more. So if you add those 2 together, you get 13. Now, yes, some of them will have 3 hydrogens, some will have 1, some will have 2. So it's a very rough estimate, but it starts to give you a ballpark of how many carbons are in your molecule. Right? So when you have no other information to go from, this rule of 13, after you subtracted the chlorines and the bromines, is a really good way to just start getting some insight into what does the molecule look like. All right. So a couple things about this. Remember, your mass is over the mass over charge. right? So it's the mass over charge. And then look for those isotope patterns, right? Your chlorines, your bromines. All right, I hope this was helpful, class.